Hi, welcome to the Module 1, Supervised Learning for Quantum Dots. In this module, we are first going to cover motivation for machine learning and tuning of quantum devices in general, with the special emphasis on the semiconductor quantum devices. Then I am going to quickly cover a quantum dot charge stability diagram to set up a language and notation for the tools we are going to be using for our machine learning tasks. And finally, we are going to look at how to use a neural network for charge stability diagram classification. And a final part of this module will be your coding demo with Arash, where you are going to implement everything we learned in the lecture and get a real hands-on feeling of what it takes of building a neural network for charge stability diagram classification. So let's get started. The structure of this module and every module that follows will be following. You will have some very general, high overflow motivation of why are we doing this, what's the reason, what are the tools. Then we are going to zero down on a very specific application. In the case of this module, this is going to be supervised learning for a configuration of quantum dots. I'm going to explain in a second exactly what I mean by this. And finally, we are going to have a hands-on coding session when you really by yourself in a Jupyter notebook implement your own neural network. This case, the neural network will be a classifier of quantum dot configurations. Throughout the course, we are going to be using a PyTorch machine learning package. Let us begin with the motivation for control and tuning of quantum devices with machine learning. So generally, when you have any type of quantum device and you want it to operate at the optimal level, basically on a very, very high abstraction level, what you have to do is to navigate some parameter optimization landscape to bring the device exactly into the sweet spot where you want it to operate, where the physics is exactly what you want it to be to observe a specific physics phenomena you want to study. You may know that if you, for example, have a very well fabricated single qubit, this is not necessarily super hard. You can just tune one voltage or some kind of drive parameter until you find just by hand this operating spot. Or you have a mathematical optimization task, but because your device is small and your number of parameters is low, you can simply just solve it with any SciPy optimizer that is available to you. The challenges come when quantum devices become bigger or more complex, and their tuning and control does become much, much harder. What happens is that your optimization parameter landscape becomes much more high dimensional, and the decisions and how to navigate in it become way more complex. And these are the type of tasks where machine learning emerged in recent years as a helpful tool. We can think of tuning of quantum devices at a different abstraction level. Throughout this course, we are going to touch two of those, so let me quickly explain what do they mean. On one hand, we can just do a feature analysis in the measured quantum data. What I mean by that is that you do your measurements and then you want to spot a specific feature in those measurements. So basically, because some smart people ahead of you did a lot of work, the real task really gets narrowed down to really a feature or image analysis. So it's almost narrowed down to just a data analysis task. Then there is a higher, more abstract level where you want to learn the parameters governing underlying physics. This means that you want to take your measurement data, but you want to learn your Hamiltonian. You want to learn some noise parameter. You want to learn something that is intrinsically, intimately related to the underlying physics that makes you measure the data you are measuring. So these are two different levels. And throughout the course, we are going to, through week 1 to 3, move on this lower level where we will figure out how to navigate in measurement data and investigate their features. So the mapping on the machine learning problem will be more or less, hopefully, straightforward. And in the final week, we are going to elevate our abstraction to the learning of the underlying physics and relate that to tuning. In the end, what we are going to do is to take some kind of measurement data. What this measurement data exactly is doesn't super much matter. It can be your charge stability diagram, about which we are going to talk in a second. It can be some transport measurement. It can be your frequency measurement, any kind of measurement data that are accessible in your experiment. You want to put that measurement data into some model. In the context of this course, it's going to be a machine learning model. And then you want that model to output something that is related to your experiment. This can be a Hamiltonian, this can be value of some parameter, or some general property of your system. And once you know this thing, it will be a useful information in your tuning routine. So you will basically move the analysis from human operator looks at the data and decides what to do next, to the machine, specifically in our case neural network or some other machine learning algorithm, will look at the data for you and decide what to do next. So this is the sort of bigger underlying vision to have in mind where we are going through these machine learning problems, and we are going to formulate specific instances of this throughout the course. Final note I want to make throughout this introduction is that of why semiconductor qubits specifically. If you Google machine learning for tuning quantum devices, the most papers that actually going to pop up are all semiconductor qubit ones. It's not exclusive, but it's a majority. And the question is why? The reason is that we have a very fundamental motivation why. Any kind of semiconductor or more generally solid-state qubit is deeply embedded in a solid-state lattice of the material that you are using to define your qubits. This is always advertised as a huge advantage to you because it is. Because we are really dealing with everything on a really like a single electron level, we have a huge advantage in terms of scaling. And because we are dealing with semiconductors, we also have a really great potential to embed our devices into standard device fabricating workflow. But all of these advantages comes with the price, and that's the tuning. All the electrons sees all the other electrons. They see the nuclear spin, they see the surrounding lattice. So you oftentimes get a pretty complex long-range interaction that can really introduce a new tuning challenges. And it's not like that you have a super clean fabricated qubit that you map by single gradient optimization exactly to the regime that you want. Because of this surrounding material complexity, there is really extra tuning challenges that come up specifically for a solid-state qubits, and that's why we are zeroing down on all of these challenges in this course specifically.